Look up. What do you see? A ceiling? A sky? Maybe the faint, familiar dust of the Milky Way. You see a boundary, a limit to your world. But what if that boundary was an illusion? What if the very concept of our galaxy was just the first tiny step on a journey so vast, so profound, that it redefines everything you believe about existence? We are about to embark on that journey. We are going to fly through every galaxy in the observable universe. Not in a spaceship, not in a dream, but through the sheer, terrifying power of human knowledge. We will travel billions of light years, witness the birth and death of cosmic empires, and confront the ultimate edge of reality. This is a story of scale, of time, and of the improbable fact that we are here to tell it. Before we engage the hyperdrive, take a moment to anchor yourself. If this journey of discovery resonates with the deep, quiet wonder inside you, if you feel the pull of the cosmos, then join our crew. Hit that like button, subscribe to Cosmo Depth, and ensure you never miss another flight into the unknown. Your support is the fuel that powers this channel, allowing us to continue mapping the most distant corners of the universe. Now, let the journey begin. Our story starts at home, in a place we call the Milky Way. It is a place of comfort, a colossal, beautiful barred spiral galaxy, a swirling metropolis of stars. Imagine it not as a flat disk, but as a vast three-dimensional city. At its heart, the central bulge, a densely packed downtown area, glows with the light of ancient redder stars. Extending from this core are the spiral arms, the suburbs of our cosmic city, where younger, bluer stars are born in clouds of gas and dust. We reside in one of these suburbs, the relatively modest Orion Arm, a safe distance from the chaotic, radiation-drenched core. The Milky Way is a dynamic system, a colossal pinwheel of light and gravity, constantly rotating. Our Sun takes about 230 million years to complete one orbit around the galactic center, a period known as a cosmic year. The last time the Sun was in this position, the supercontinent Pangea was just beginning to break apart on Earth. This immense timescale is the first hint of the true scale of our journey. To truly appreciate the scale of our home, we must first understand its dimensions. The Milky Way stretches approximately 100,000 light-years from one edge to the other. A light-year, of course, is the distance light travels in one Earth year, nearly 6 trillion miles. To cross our galaxy, even at the speed of light, would take 100 millennia. Yet, this entire, incomprehensible structure, this stellar island containing between 100 and 400 billion suns, is merely a single grain of sand on the cosmic beach. The sheer volume of the Milky Way is a concept that requires a moment of quiet contemplation. If our solar system, with the Sun at the center and the orbit of Neptune as its boundary, were shrunk to the size of a single grain of sand, the Milky Way would be a desert stretching across the entire North American continent. The stars are not close. They are separated by gulfs of vacuum so profound that even the light from our nearest stellar neighbor, Proxima Centauri, takes over 4 years to reach us. This isolation is the norm, not the exception, and it is what makes the impending galactic collision so spectacular. The Milky Way's central region is a place of extreme density and energy. At its very heart lies Sagittarius A, pronounced A star, a supermassive black hole with a mass 4 million times that of our Sun. This black hole is the gravitational anchor for the entire galaxy. While it is currently in a relatively quiet state, its past activity has been traced through colossal, invisible structures known as the Fermi bubbles, two enormous lobes of gamma-ray emission extending 25,000 light-years above and below the galactic plane. These bubbles are evidence of past violent outbursts from Sagittarius A, a reminder that the core of our galaxy is a powerful, dynamic engine. The energy released in these events is equivalent to hundreds of thousands of supernovae, shaping the very environment of the galaxy's halo. The study of the orbits of stars closest to Sagittarius A has provided the most compelling evidence for the existence of supermassive black holes, a triumph of precision astronomy. The star S2, for instance, whips around the black hole in a mere 16 years, its speed reaching nearly 3% of the speed of light at its closest approach. This dance is a direct observation of Einstein's general relativity in action. The black hole's influence extends far beyond its immediate vicinity, dictating the motions of stars in the central bulge and contributing to the overall stability of the galactic disk. For decades, we believed our galaxy was a lone, majestic entity, a solitary queen reigning over a dark void. We were wrong. The Milky Way is not alone. It is the dominant member of a small, gravitationally bound collection of galaxies known as the local group. This group is our immediate neighborhood, a cosmic cul-de-sac where the gravitational dance of a few dozen galaxies dictates the fate of all within it. The local group is a gravitational family, a collection of galactic siblings, cousins, and distant relatives, all tied together by the invisible threads of gravity. It spans about 10 million light-years, a vast yet relatively intimate corner of the cosmos. The total mass of the local group is estimated to be around 1.2 times 10 to the power of 12 solar masses, with the vast majority of that mass being dark matter. The undisputed rival to the Milky Way's dominance is the Andromeda Galaxy, or M31. Andromeda is a behemoth, an even larger spiral galaxy, estimated to contain over 1 trillion stars, more than twice the population of our own. It is the most distant object visible to the naked eye, a faint fuzzy patch of light that has travelled for 2.5 million years to reach your retina. When you look at Andromeda, you are seeing light that began its journey before the first hominids walked the Earth. But the light we see is not just a picture of the past, it is a warning of the future. Andromeda is not a distant, passive neighbour. It is a colossal, incoming freight train. It is hurtling toward us at a speed of approximately 110 kilometers per second, or about 246,000 miles per hour. This is not a slow drift. This is a head-on collision course. In about 4.5 billion years, the Milky Way and Andromeda will meet. This is the first great cosmic drama of our journey, a gravitational ballet that will redefine our galactic home. The current distance between us is about 2.5 million light-years, a gap that is closing rapidly by cosmic standards. The precise measurement of Andromeda's tangential velocity, the sideways motion, was a crucial step in confirming this collision course, a feat accomplished by the Hubble Space Telescope. The term collision is misleading. When two galaxies of this magnitude meet, the vast, empty space between the stars means that very few, if any, stars will actually strike one another. Instead, the two galaxies will pass through each other, their immense gravitational fields tearing, stretching, and reshaping the other. Imagine two colossal clouds of smoke passing through each other, their individual particles rarely touching, but the overall structure becoming irrevocably merged. This process will repeat over hundreds of millions of years, until the two spirals finally coalesce into a single, massive, elliptical galaxy, which astronomers have already nicknamed Milky Way. The process of the Milky Way merger is a spectacular, drawn-out affair. First, the two galaxies will approach, their halos of dark matter beginning to interact. The gravitational tides will pull long streams of stars and gas out of both galaxies, forming colossal, glowing tails that stretch across the intergalactic void. The night sky on Earth, if it still exists, will be a spectacle of unimaginable beauty, dominated by the swirling, distorted shape of the incoming Andromeda. The first pass will be a chaotic, violent dance, flinging some stars out into the void and forcing others into new, eccentric orbits. The second and third passes will complete the merger, settling the two spirals into a single, massive, football-shaped, elliptical galaxy. The star formation rate will temporarily spike as the gas clouds are compressed, creating a final, brilliant burst of new stars before the gas is exhausted. This is not an end, but a violent, spectacular transformation, a cosmic rebirth. Our Sun, along with its planets, will likely be flung into a new, much more distant orbit around the center of Milky Way, but the solar system itself will remain intact. The two supermassive black holes, Sagittarius A star and Andromeda's central black hole, will spiral toward each other in a gravitational death dance, eventually merging to form a single, even more colossal black hole, releasing a burst of gravitational waves that will ripple across the cosmos. This final merger will be the ultimate gravitational event in our local history, a cataclysm that will shake the very foundations of the new galaxy. But the local group is more than just two giants. It is a collection of smaller, less glamorous galaxies, mostly dwarf ellipticals and irregulars, that orbit the two main players like celestial moths. The Triangulum Galaxy, M33, is the third largest, a beautiful, smaller spiral that may or may not be gravitationally bound to Andromeda. Then there are the Magellanic Clouds, the large and small, two irregular dwarf galaxies that are currently being tidally stripped and consumed by the Milky Way's immense gravity. This is galactic cannibalism on a small scale, a process that has happened countless times in our galaxy's history, with the remnants of smaller galaxies now forming the faint, ghostly streams of stars in our halo. These tidal streams are like cosmic archaeological sites, revealing the history of our galaxy's growth through the consumption of its smaller neighbors. The Magellanic Clouds, in particular, are leaving a massive trail of gas behind them, a stream that stretches across a quarter of the sky, a visible sign of the Milky Way's gravitational dominance. The local group is a constant battleground of gravitational forces, where the strong devour the weak. The dwarf galaxies are the most numerous type of galaxy in the universe, and their study provides crucial clues about the formation and evolution of the larger spirals. The smallest of these, like the Segway 1 dwarf galaxy, are almost entirely dark matter, containing only a few hundred stars, making them the purest examples of dark matter halos we have observed. what holds this entire structure together? What dictates the speed and direction of this colossal dance? The answer is something we cannot see, something that makes up the vast majority of the mass in the local group: dark matter. We cannot observe dark matter directly because it does not interact with light. It is invisible, transparent, and silent. Yet, its gravitational influence is undeniable. The evidence for dark matter is overwhelming, coming from multiple lines of observation. The rotation curves of galaxies, the gravitational lensing of distant objects, and the cosmic microwave background. If the Milky Way contained only the visible stars, gas, and dust, it would spin so fast that it would fly apart. The outer stars are moving far too quickly for the visible mass to hold them in orbit. The only explanation is that the entire local group is encased in a massive, invisible, dark matter halo, a spherical cloud of this mysterious substance that provides the gravitational scaffolding for all the visible matter. It is the skeleton of the universe, and we are merely the luminous skin stretched over it. The dark matter halo of the Milky Way is estimated to be 10 times the mass of all its stars and gas combined, extending far beyond the visible disk. This invisible mass is the true anchor of our home. The nature of dark matter remains one of the most profound mysteries in physics, a silent, invisible force that governs the fate of the cosmos. The search for the dark matter particle, whether it be a WIMP, weakly interacting massive particle, or an axion, is one of the most active and challenging areas of modern science, involving massive underground detectors shielded from all other forms of radiation. This dark matter halo is the true boundary of our local neighborhood, a gravitational sphere of influence extending far beyond the visible disk of the Milky Way. To truly leave our home, we must punch through this invisible barrier, and as we do, the scale of the universe will once again shatter our perception. The local group, this tiny cluster of galaxies, is merely the first stop on our journey, a testament to the power of gravity to organize matter even in the vastness of space. We are now leaving the local group, accelerating past the dwarf galaxies that mark its outer edge. The Milky Way and Andromeda shrink behind us, two magnificent spirals locked in their slow, inevitable embrace. Ahead, the darkness is not empty. It is filled with a faint, distant glow of thousands of other galaxies, all streaming toward a single, colossal point in space. We are now entering the realm of the Virgo cluster. The sheer scale of this initial leg of the journey is a lesson in humility. We have traveled a mere 3 million light years, yet we have already encountered forces and structures that dwarf our imagination. The local group, our cosmic island, is a microcosm of the universe's grand design, a place where the fundamental forces of gravity and dark matter are already dictating the fate of trillions of stars. The impending Milkomeda collision is not a disaster. It is a cosmic birth, the next stage in the evolution of matter. It is a reminder that the universe is constantly recycling, constantly reshaping itself, and that nothing, not even a galaxy, is permanent. Our journey is a witness to this eternal process. We leave behind the familiar, the known, and venture into the truly unknown. The space between the local group and the Virgo cluster is not a void, but a vast, tenuous sea of intergalactic gas, threaded with faint streams of stars, the debris of ancient, long-consumed dwarf galaxies. This is the realm of the cosmic web scaffolding, the invisible architecture that guides the flow of matter. Our velocity increases, driven by the gravitational pull of the massive cluster ahead. The faint, distant light of the Virgo cluster begins to resolve itself, transforming from a hazy glow into a swarm of individual galaxies, each one a stellar empire, each one a destination on our ultimate journey. The true scale of the universe is about to be revealed. The local group is just a tiny tributary flowing into the massive river of the Virgo supercluster. Our next destination is the heart of that river, a place of unimaginable density and power. The journey continues, and the scale of the cosmos only grows more overwhelming. The light we are now seeing from the Virgo cluster left those galaxies 54 million years ago, a time when mammals were just beginning to diversify on Earth. We are not just traveling through space, we are traveling through a vast, living history book written in light. The next chapter is about to begin. The journey from the local group to the Virgo cluster is the first true measure of cosmic distance. We are traveling approximately 54 million light years. To put that into perspective, the light we are now passing left these galaxies when the first hominids were just beginning to walk upright on Earth. We are traversing a gulf of time and space that is almost impossible to comprehend. And yet, this is still considered our immediate cosmic vicinity. The scale is already beginning to dwarf our imagination, but this is merely the beginning of the cosmic river we are navigating. The Virgo cluster is the next great gravitational landmark on our map. It is the nearest major cluster of galaxies, a true metropolis containing over 1,300 and possibly as many as 2,000 individual galaxies. Unlike the relatively sparse local group, the Virgo cluster is a dense, crowded environment, a place of constant interaction, violence, and transformation. It is a galactic pressure cooker, where the forces of gravity and environment shape the evolution of every galaxy within its influence. The cluster spans about 15 million light-years, a colossal sphere of gravitational influence that dominates our local region of space. As we approach, the view is overwhelming. Instead of a few isolated spirals, the sky is filled with a swarm of galaxies, giant ellipticals, magnificent spirals, and countless smaller, irregular systems. The cluster is dominated by three massive elliptical galaxies at its core: M87, M86, and M49. These are the ancient, bloated kings of the cluster, having grown to their immense size by consuming countless smaller galaxies over billions of years. They are the result of a long history of galactic mergers, their smooth, featureless appearance a testament to the violence of their past. The color of these central ellipticals is a deep reddish yellow, a sign that they are composed primarily of old, dying stars, having long since exhausted their fuel for new star formation. M87, in particular, is a spectacle of cosmic power. It is a supergiant elliptical galaxy, one of the most massive galaxies in the local universe, containing trillions of stars. At its center lies a supermassive black hole, one of the largest ever directly imaged, with a mass equivalent to 6.5 billion suns. This black hole is not passive. It is an engine of destruction, firing a colossal, relativistic jet of plasma that stretches for thousands of light years into space. This jet, moving at nearly the speed of light, is a testament to the sheer, raw energy that can be unleashed at the heart of a galactic core. The energy output of this jet is so immense that it carves out colossal bubbles in the surrounding intergalactic gas, influencing the star formation of galaxies hundreds of thousands of light years away. The sheer power of M87's black hole is a chilling reminder of the destructive forces that lurk at the heart of every large galaxy. The jet itself is a stream of highly energetic particles visible across the electromagnetic spectrum, from radio waves to X-rays, a beacon of cosmic violence. The black hole at the center of M87 is an active galactic nucleus, AGN, a powerhouse that regulates the growth of the entire cluster by heating the surrounding gas and preventing it from cooling and forming new stars. The Event Horizon Telescope collaboration, which produced the first image of a black hole, also captured the shadow of M87's black hole, a direct visual confirmation of this cosmic giant. The environment within the Virgo cluster is harsh. Galaxies here are not just drifting, they are moving at high velocities through a superheated thin plasma known as the intracluster medium, ICM. This medium, heated to millions of degrees by the gravitational collapse of the cluster, acts like a cosmic headwind. As spiral galaxies plunge through the ICM, the pressure of the gas strips away their own cold star-forming gas and dust in a process called ram pressure stripping. Imagine a jellyfish swimming through a dense fluid, its tentacles being dragged behind it. That is what happens to a spiral galaxy in the Virgo cluster. Its beautiful star-forming arms are ripped away, leaving behind a trail of glowing gas. Over time, these galaxies are sterilized, their fuel for new star formation gone, turning them into red, dead, elliptical, or lenticular galaxies. This is the brutal, transformative power of the cluster environment, a process that explains why the center of the Virgo cluster is dominated by these ancient gas-poor ellipticals. The cluster environment is a galactic evolutionary accelerator, forcing galaxies to mature and die much faster than their isolated counterparts. The ICM itself is a source of diffuse X-ray emission, a ghostly glow that permeates the entire cluster, revealing the immense amount of energy locked up in this superheated plasma. The study of this X-ray gas is one of the primary ways we can map the distribution of dark matter within the cluster, as the gas is held in place by the dark matter's gravitational pull. The Virgo cluster is not the end of the line. It is merely the core of an even larger structure, the Virgo supercluster, which we now know is only a small lobe of a much grander structure. For decades, the Virgo supercluster was considered our ultimate cosmic address. It was the largest structure we could map, a vast flattened pancake of galaxies, with the Virgo cluster at its center and our local group residing on one of its outer fringes. It was the largest structure we could conceive of, a massive gravitationally bound entity. But the universe is far more complex, and our map was incomplete. In 2014, a team of astronomers redefined our cosmic home, mapping the true gravitational boundaries of our region of space. They discovered that the Virgo supercluster is just a minor appendage of a truly colossal structure, the Laniakea supercluster. Laniakea, a name derived from the Hawaiian for immeasurable heaven, is our true galactic continent. It is a massive, sprawling structure, over 520 million light-years across, containing approximately 100,000 galaxies. The key to defining Laniakea was not simply mapping the location of galaxies, but mapping their motion. In the vastness of space, galaxies are not just moving randomly. They are flowing like water down a massive, invisible gravitational watershed. Every galaxy within Laniakea is moving inward toward a single, massive gravitational center. This is the cosmic equivalent of a river basin, where all the tributaries flow toward the main channel. The flow is subtle, a gentle but relentless tug that dominates the motion of every galaxy in this vast region. The mapping of this flow required measuring the peculiar velocities of thousands of galaxies, subtracting the expansion of the universe to reveal the underlying gravitational pull. This revolutionary mapping technique, known as the Cosmic Flows Project, showed that our entire local region is part of a single, coherent, flowing structure. The boundaries of Laniakea are defined by the points where the flow of galaxies diverges, where the gravitational pull of other superclusters takes over. The central channel of this flow is the most mysterious and compelling part of our journey: the Great Attractor. The Great Attractor is not a single object, but a massive, diffuse concentration of matter, a supercluster, located approximately 150 to 250 million light-years away. It is the gravitational heart of Laniakea, the point toward which our Milky Way, the entire local group, the Virgo cluster, and all 100,000 galaxies of Laniakea are streaming at speeds of hundreds of kilometers per second. We are all falling toward it, an entire galactic continent in a slow, inevitable gravitational descent. The Great Attractor is the most massive structure in our local universe, a gravitational sink that is pulling everything in its vicinity toward it. The Great Attractor is a perfect example of the universe's hidden power. For decades, it was almost impossible to study because it lies directly behind the plane of our own Milky Way. The dense gas and dust in our galaxy's disk block out the light from everything behind it, creating a region of the sky astronomers call the zone of avoidance. It was only through the use of infrared and X-ray telescopes, which can penetrate this veil of dust, that we were able to map the immense concentration of matter that is pulling us in. The Great Attractor is a testament to the power of dark matter, which is the primary source of its immense gravitational pull. The visible galaxies we see in that direction are only the luminous tip of a colossal, invisible iceberg of dark matter. The true nature of the Great Attractor is still being uncovered, but it is clear that it is the dominant gravitational force in our corner of the cosmos. Further mapping has revealed that the Great Attractor is part of an even larger, more massive structure called the Shapley supercluster, a colossal concentration of matter that is the largest known structure in the nearby universe, and a major component of the gravitational pull we feel. As we fly toward this gravitational nexus, we are witnessing the fundamental force of gravity at its most powerful, organizing the universe on a scale that dwarfs our previous understanding. Laniakea is a testament to the organizing principle of dark matter, which forms the invisible scaffolding that allows these massive structures to coalesce. But even Laniakea is not the end of the map. It is merely one bright knot in a much larger, darker tapestry. We must now leave the familiar territory of our supercluster and venture into the truly vast, three-dimensional structure that defines the entire cosmos. We are about to enter the cosmic web. The journey through Laniakea has shown us that our local universe is a dynamic, flowing system, where gravity dictates the motion of entire galactic continents. The next stage of our journey will reveal the ultimate architecture of the universe, the colossal structure that contains Laniakea and all other superclusters. The scale is about to become truly mind-bending. We are leaving the river basin and entering the vast, interconnected network of the cosmic sponge. The structures we are about to encounter are so large that the light from one end takes billions of years to reach the other. The journey through Laniakea has shown us that galaxies are not scattered randomly like confetti. They are organized, flowing, and structured. But the cosmic web is where this organization reaches its ultimate mind-bending scale. This is the largest known structure in the universe, the grand three-dimensional architecture that dictates the distribution of all matter. Imagine the universe not as a uniform expanse, but as a colossal, three-dimensional sponge or a foam. The matter in the universe, the galaxies, the clusters, the superclusters, is concentrated along the thin, thread-like walls and strands of this foam. These threads are the filaments, and the vast, empty bubbles they enclose are the voids. This is the cosmic web, the largest known structure in the universe, and it is the result of gravity acting on the tiny quantum fluctuations of the early universe over 13.8 billion years. The entire structure spans billions of light years, a colossal network that connects every major structure we have encountered so far. As we fly out of Laniakea, the density of galaxies begins to thin, and the structures become more elongated. We are now traversing one of the great filaments, a superhighway of galaxies that connects Laniakea to other superclusters. These filaments can stretch for hundreds of millions of light years, acting as the arteries of the universe, channeling matter toward the densest knots, which are the galaxy clusters we just left. These filaments are not just lines of galaxies. They are colossal gravitational troughs, where the density of dark matter is slightly higher than the cosmic average, providing the necessary gravitational pull to shepherd galaxies into their massive congregations. The gas in these filaments is incredibly hot and diffuse, forming the warm-hot intergalactic medium, WIM, which is thought to contain a significant fraction of the universe's ordinary matter that has yet to collapse into galaxies. The WIM is a ghostly, almost invisible component of the universe, only detectable through its faint X-ray emission and the absorption lines it imprints on the light of distant quasars. The study of the WIM is crucial because it represents the missing baryon problem, the fact that we cannot account for all the ordinary matter predicted by the Big Bang Theory in the form of stars and galaxies. The WIM is the likely reservoir for this missing matter, a vast, diffuse sea of plasma that makes up the majority of the universe's normal matter. The existence of the cosmic web is a direct consequence of dark matter. Computer simulations show that without dark matter, the universe would be a uniform, featureless soup of gas. It is the dark matter that first collapsed into these filamentary structures, forming the gravitational potential wells that then drew in the ordinary, visible matter, the hydrogen and helium gas, which eventually cooled and condensed to form the first stars and galaxies. The cosmic web is, in essence, the fossilized imprint of the dark matter distribution in the universe. It is the invisible skeleton upon which the luminous body of the cosmos is draped. The structure of the web is a direct reflection of the tiny density fluctuations present in the universe just moments after the Big Bang, amplified by gravity over billions of years. The largest known structure in the cosmic web is the Hercules Corona Borealis Great Wall, a colossal sheet of galaxies and clusters stretching over 10 billion light-years, a structure so large that it challenges the cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales. But for every bright, crowded filament, there is a vast, terrifying emptiness. The voids. The voids are the most desolate places in the cosmos. They are colossal, spherical regions, often hundreds of millions of light years across, that are almost entirely devoid of galaxies. While they are not perfectly empty, they contain a tiny fraction of the average matter density. They are the closest thing to true nothingness we can find. The largest of these, the giant void in the constellation Canis Venatici, is over 1 billion light-years across. To put that in perspective, 1 billion light-years is roughly 10,000 times the diameter of our own Milky Way galaxy. To fly through a void is to experience the ultimate isolation. The nearest galaxy might be 100 million light-years away, a faint, ghostly smudge in the distance. This is where the universe truly earns its name as a vacuum. The voids are the spaces between the bubbles of the cosmic foam, and they represent the regions where the initial density of matter in the early universe was slightly lower than average. Gravity, over time, has simply drained these regions, pulling the few galaxies they contained toward the surrounding filaments. The voids are the great cosmic deserts, a chilling reminder of the universe's vast, uncaring scale. The few galaxies that do exist in the voids are often isolated, pristine systems, untouched by the violent mergers and ram pressure stripping that characterize the cluster environment. They are cosmic relics, preserved in the emptiness, and their study provides a unique laboratory for understanding galaxy evolution in the absence of external influences. The voids are not just empty. They are actively growing, being pushed apart by the relentless force of dark energy. The cosmic web is not a static structure. It is being stretched, pulled, and ultimately torn apart by the most mysterious force in all of physics: dark energy. Dark energy is the dominant component of the universe, making up about 68% of its total energy density. It is a repulsive force, a kind of anti-gravity that is causing the expansion of the universe to accelerate. For the first few billion years after the Big Bang, gravity was the dominant force, pulling matter together to form the first stars, galaxies, and the cosmic web. But as the universe expanded and the matter density thinned, dark energy, which is a property of space itself, began to take over. The effect of dark energy is subtle on small scales. It cannot pull apart the stars in a galaxy or the galaxies in the local group, but on the scale of the cosmic web, its influence is absolute. It is actively pushing the filaments and superclusters away from each other, widening the voids and stretching the entire structure of the universe. The cosmic web is slowly being dissolved by the very fabric of space. This accelerating expansion is the most profound discovery of modern cosmology, fundamentally changing our understanding of the universe's past and future. The nature of dark energy is still unknown, but the leading candidate is the cosmological constant, a form of energy inherent to the vacuum of space itself, a concept first introduced by Einstein and later resurrected to explain the accelerating expansion. The precise measurement of the acceleration rate, known as the Hubble constant, is one of the most important and contentious measurements in modern cosmology, with different methods yielding slightly different results. A tension that hints at new physics beyond our current understanding. As we fly through the cosmic web, we are witnessing a cosmic tug of war. Gravity is desperately trying to hold the knots and threads together, while dark energy is relentlessly trying to pull the entire tapestry apart. This battle is the defining feature of the modern universe, and it has profound implications for our journey. The accelerating expansion means that the galaxies we are flying toward are not just moving away from us due to the Big Bang. They are being pushed away at an ever-increasing rate. The light from the most distant galaxies has been traveling for so long that the space it is traveling through has stretched dramatically. This stretching of space is what causes the light to shift toward the red end of the spectrum, a phenomenon known as cosmological redshift. The further we look, the greater the redshift, and the faster the galaxy appears to be receding. This is not a speed through space, but the speed at which the space between us and the galaxy is expanding. We are now approaching the limit of what we can see, the boundary where the expansion of space becomes so rapid that the light from those galaxies will never, ever reach us. We are flying toward the edge of the observable universe. The cosmic web is the last great structure before we enter the realm of the truly ancient, the realm of the deep field, where we will look back in time to the very beginning of the galaxies. We have left the familiar structures of the cosmic web behind. The filaments are now faint, and the voids are immense. The density of galaxies has dropped dramatically, and the light we are seeing is no longer a snapshot of the present, but a memory of the deep past. We are entering the realm of the deep field, the region of space where every point of light is not just a galaxy, but a window into the universe's infancy. To look this far out is to look back in time. The light from the galaxies we are now passing has been traveling for over 10 billion years. It left its source when the Earth was not yet formed, when the Sun was still a young star, and when the Milky Way was a chaotic, rapidly assembling proto-galaxy. We are no longer just flying through space, we are traveling through time itself. This is the concept of look-back time, the fundamental principle of observational cosmology. The further we look, the further back in time we see. The most distant galaxies we observe are not just far away, they are incredibly young, showing us the universe as it was when it was only a fraction of its current age. The light from these galaxies has been stretched by the expansion of space, a phenomenon so profound that it shifts the light from the visible spectrum into the infrared. The galaxies in this region are different. They are not the grand, well-formed spirals and ellipticals of the local group. They are smaller, more chaotic, and intensely blue. They are the starburst galaxies, furiously creating new stars at rates hundreds of times higher than the Milky Way does today. This was the era of peak star formation, the time when the universe was most active and most violent, a period astronomers call the cosmic noon. The blue color is a signature of massive, hot, short-lived stars that dominate the light output of these young, energetic systems. These galaxies are the building blocks of the massive structures we see today, constantly merging and growing, fueled by vast reservoirs of cold gas. The sheer density of star formation in these early galaxies is a testament to the chaotic, rapid assembly of the first cosmic structures. The most profound discoveries in this region have been made by the James Webb Space Telescope, JWST. JWST is not just a telescope, it is a time machine. Because the light from these early galaxies is so highly redshifted, stretched from visible light into the infrared spectrum by the expansion of space, we needed a telescope capable of seeing in infrared with unprecedented clarity. JWST is that instrument, a marvel of engineering that has pushed the boundaries of our vision to the very edge of time. Its massive, gold-coated mirror and cryogenically cooled instruments allow it to capture the faint, stretched light from the earliest moments of the universe. The sensitivity of JWST is so great that it can detect the heat signature of a bumblebee on the moon. The discoveries have been nothing short of revolutionary. We expected to find small, primitive, and disorganized baby galaxies in the early universe. Instead, JWST has revealed galaxies that are surprisingly massive, bright, and mature, existing only a few 100 million years after the Big Bang. This has forced a fundamental re-evaluation of our models of galaxy formation. Take, for example, the galaxy JD's GS Z14.0. This is the current record holder, a galaxy observed at a redshift of 14.32. The light we are now seeing left this galaxy when the universe was only about 290 million years old. To put that in perspective, if the universe's age were compressed into a single calendar year, we are looking at the first week of January. What is astonishing is that JD's GSZ 14-0 is not a tiny smudge. It is a relatively large, luminous galaxy already containing billions of stars. Its existence challenges our fundamental models of cosmology. How could gravity assemble so much matter so quickly? Where did the heavy elements needed for its stars come from? These early, mature galaxies suggest that the process of galaxy formation began much earlier and proceeded much faster than we ever thought possible. They are the unexpected giants of the early universe, forcing us to rewrite the cosmic history books. The presence of heavy elements, which are only forged in the hearts of massive stars that live and die quickly, suggests that the first generation of stars, the so-called population 3 stars, must have formed and died even earlier than we thought. These population 3 stars, composed only of hydrogen and helium, are theorized to have been hundreds of times the mass of our Sun, living fast and dying young in spectacular supernovae that seeded the universe with the first heavy elements. The JWST is actively searching for the light of these elusive first stars, the true pioneers of the cosmos. The discovery of these massive early galaxies has led to the hypothesis of dark matter-free star formation, where the first stars formed in regions of the universe that were not yet dominated by dark matter halos, a radical departure from the standard model. As we fly past these ancient lights, we are witnessing the process of cosmic dawn, the moment the first stars and galaxies ignited, ending the long, dark age that followed the Big Bang. The light from these first objects reionized the neutral hydrogen gas that filled the early universe, making the cosmos transparent and allowing light to travel freely. We are seeing the universe transition from darkness to light, a profound transformation that set the stage for all subsequent cosmic evolution. This reionization epoch is one of the most active areas of research, and the JWST is providing the first direct glimpses into this crucial period, revealing the patchy, uneven way in which the universe was relit. The reionization process was a violent, energetic event, driven by the intense ultraviolet radiation from the first stars and quasars, fundamentally changing the state of matter in the universe. But the journey must continue, and the galaxies are becoming fewer and fainter. The redshift is now extreme, pushing the light further and further into the infrared. We are approaching the point where the expansion of space is so rapid that the light has been stretched almost to the breaking point. The galaxies are receding from us at speeds approaching the speed of light, not through space, but because the space between us is expanding so rapidly. We are nearing the ultimate boundary of the observable universe, a wall of fire that marks the end of our visible journey. This boundary is not a physical wall, it is a limit of time. We cannot see beyond a certain point, because before that time, the universe was opaque. We are about to confront the cosmic microwave background, CMB, the last light we will ever see on this journey, the ultimate echo of the Big Bang itself. The galaxies have vanished. The space around us is dark, save for a faint, uniform glow that permeates everything. We have reached the cosmic microwave background, the oldest light in the universe, and the ultimate horizon of our journey. This is the light that has traveled for 13.8 billion years to reach us, and it marks the moment the universe became transparent. The CMB is the afterglow of the Big Bang, a relic of a time when the universe was only 380,000 years old. Before this moment, the universe was a superheated dense plasma, a fog of protons, electrons, and photons. The temperature was so high, around 3000 Kelvin, that electrons could not bind to atomic nuclei. Photons, the particles of light, was constantly scattering off the free electrons, trapped in a perpetual pinball machine. The universe was opaque, like the inside of a star. This was the plasma epoch, a time of intense heat and density where light could not travel more than a few centimeters before being scattered. Then the universe expanded and cooled. When the temperature dropped below 3000 Kelvin, the electrons finally combined with the nuclei to form the first neutral atoms, primarily hydrogen and helium. This event is known as recombination. Suddenly, the photons were free to travel unimpeded. The universe became transparent. This moment, the surface of last scattering, is what we are now seeing. It is a spherical shell of light surrounding us, a cosmic baby picture of the universe at 380,000 years old. The light we are now seeing is those very first photons, released 13.8 billion years ago. They have been traveling ever since, and the expansion of space has stretched their wavelength from visible light, the color of a dim, red star, all the way into the microwave portion of the electromagnetic spectrum. This is why we call it the cosmic microwave background. Its current temperature is a frigid 2.725 Kelvin, just a few degrees above absolute zero. The discovery of the CMB in 1964 by Arno Penzias and Robert Wilson who initially mistook the signal for pigeon droppings in their antenna, was one of the most significant pieces of evidence confirming the Big Bang theory. The CMB is the most perfect blackbody spectrum ever measured in nature. It is almost perfectly uniform, a testament to the incredible smoothness of the early universe. But the word "almost" is the key. Embedded within this uniform glow are tiny, minuscule temperature fluctuations, variations of only 1 part in 100,000. These tiny ripples are the most important map in all of cosmology. They are the seeds of structure. The slightly hotter, denser regions in the CMB are the places where gravity had a tiny head start. Over billions of years, these tiny density enhancements grew, pulling in more and more matter, eventually collapsing to form the dark matter halos, the filaments of the cosmic web, the superclusters, and ultimately, the galaxies we just flew through. The CMB is the blueprint of the entire universe, a fossil record of the initial conditions that led to everything we see today. The study of these fluctuations through missions like COBE, WMAP, and Planck has allowed us to determine the age, composition, and geometry of the universe with unprecedented accuracy. The pattern of these ripples, known as the acoustic peaks, is a direct imprint of sound waves that traveled through the plasma before recombination, providing a cosmic ruler for measuring the universe. The precise shape of these peaks tells us that the universe is flat, meaning that parallel lines will never meet, and that the total energy density of the universe is exactly equal to the critical density required to halt the expansion. We cannot see beyond the CMB. It is a fundamental limit of our vision, a wall of fire that marks the beginning of the opaque, plasma-filled universe. To look further back in time would require us to use something other than light, such as gravitational waves or neutrinos, which were able to travel freely much earlier. The era before the CMB, the Dark Ages, is the next great frontier of cosmology, a time when the universe was filled with neutral hydrogen and had yet to form its first stars. The period of cosmic inflation, a brief exponential expansion of the universe in the first fraction of a second after the Big Bang, is theorized to have smoothed out the universe and created the initial quantum fluctuations that we see imprinted on the CMB. The search for primordial gravitational waves, which would be a direct signature of inflation, is one of the holy grails of modern cosmology. But the journey is not over. We have reached the edge of the observable universe, but the universe itself does not end here. The observable universe is simply the part of the cosmos from which light has had time to reach us. The universe in its entirety is almost certainly much, much larger, perhaps infinitely so. As we hover at this cosmic horizon, we must confront the philosophical implications of our journey. We have mapped a sphere of reality 93 billion light-years across, containing an estimated 2 trillion galaxies. And yet, this entire, mind-boggling volume is only a fraction of the whole. What lies beyond the CMB? What lies beyond the edge of the observable universe? We cannot see it, but we can reason about it. The universe beyond our horizon is likely more of the same. More galaxies, more clusters, more cosmic web, all governed by the same laws of physics. But the light from those galaxies will never reach us, because the space between us and them is expanding faster than the speed of light. They are forever beyond our reach, receding into their own private, unobservable universe. This realization is the true climax of our journey. We have flown through every galaxy we can see, only to discover that the total number of galaxies is unknowable, perhaps infinite. We have reached the limit of our senses, but not the limit of reality. We have mapped our cosmic bubble, and now we must contemplate the vastness that lies beyond. The observable universe is our cosmic prison, a sphere of light and time that we can never truly escape. We turn our gaze from the faint ancient light of the CMB and look forward, billions and trillions of years into the future. The universe we have just mapped is a vibrant, active place, full of collisions, star formation, and the gravitational dance of superclusters. But the future is one of profound, accelerating decay, a slow, inexorable march toward silence and cold. The dominant force in the universe is now dark energy. Its repulsive pressure is not just stretching the cosmic web, it is actively isolating every galaxy outside of our immediate gravitational neighborhood. The expansion of space is accelerating, and the galaxies are being pushed away from us at an ever-increasing rate. This is the ultimate triumph of dark energy over gravity on the largest scales. In the next few billion years, the Milky Way and Andromeda will complete their merger, forming the massive elliptical galaxy, Milkomeda. This will be the last great burst of activity in our local region. The gas and dust will be stirred up, triggering a final wave of star formation, and the two supermassive black holes will spiral into each other, creating a colossal gravitational wave event that will ripple across the cosmos. This merger is the final act of gravity on the largest scale in our local vicinity, a spectacular, violent end to the two great spirals. The resulting Milkomeda will be a red and dead galaxy, its star formation fuel largely consumed in the merger, a monument to the fleeting nature of spiral galaxies. But outside of Milkomeda, the universe is already beginning to empty. The galaxies that are not gravitationally bound to our new supergalaxy are being pushed away by the accelerating expansion of space. They are crossing the cosmological event horizon, the point of no return. Once a galaxy crosses this horizon, its light will be stretched so severely that it will become undetectable, and eventually, the galaxy itself will be receding faster than the speed of light relative to us. This is not a journey, it is a permanent, irreversible isolation. The event horizon is not a physical barrier, but a boundary in time, a consequence of the ever-increasing rate of expansion. The light from these galaxies is still traveling, but the space it is traveling through is expanding so fast that the light will never reach us. In 100 billion years, the universe will be unrecognizable. All the galaxies we have just flown through, the Virgo cluster, the Laniakea supercluster, the distant starbursts, will have vanished from our sky. They will not have moved. The space between us and them will have expanded so much that their light can no longer bridge the gap. Milkomeda will be an island universe, alone in a vast, empty, black void. The night sky will be utterly dark, save for the stars of our own merged galaxy. Future astronomers, if they exist, will have no way of knowing that other galaxies ever existed. They will look out and see only the darkness, and they will conclude that their galaxy is the entire universe. All the evidence for the Big Bang, for the expansion of space, and for the existence of the cosmic web will have been erased from the sky. The history of the universe will be lost to them. a cosmic tragedy of epic proportions. This is the Big Freeze, or the heat death of the universe. It is a slow, inexorable march toward maximum entropy. The universe will become so spread out that no energy can be transferred, and the temperature will approach absolute zero. As the eons pass, the stars within Milkomeda will exhaust their nuclear fuel. The smaller, longer-lived stars, the red dwarfs, will burn out last, leaving behind white dwarfs, neutron stars, and black holes. Star formation will cease entirely as the remaining gas and dust are locked up in stellar remnants. In 1 trillion years, the last stars will have faded. The galaxy will be a graveyard of cold, dark stellar corpses. The only light will come from the occasional collision of two white dwarfs, triggering a brief, final supernova. But even these remnants are not eternal. Over unimaginable timescales, trillions upon trillions of years, the stellar remnants themselves will be ejected from the galaxy by gravitational encounters, flung out into the cold, empty intergalactic void. The supermassive black hole at the center of Milkomeda will grow, consuming everything that falls into it. Finally, the black holes themselves will evaporate through Hawking radiation. This process is incredibly slow, taking an estimated 10 to the power of 100 years for a stellar mass black hole. The supermassive black hole at the core will take even longer, perhaps 10 to the power of 106 years. The universe will be a cold, dark expanse of photons, neutrinos, and the occasional electron or positron, separated by vast, expanding distances. The final state of the universe is a state of utter, cold, dark equilibrium. The journey through every galaxy in the observable universe ends not with a bang, but with the ultimate silent whimper of the Big Freeze. It is a somber, terrifying conclusion, but it is the scientifically predicted fate of the cosmos we inhabit. This fate, however, is what makes our present moment so precious. We exist in the brief, fleeting window of time when the universe is still vibrant, when the galaxies are still close enough to see, and when the light from the Big Bang is still reaching us. We are the conscious observers of the cosmic drama, and our ability to map this vastness is our greatest triumph. The universe is telling us its story, and we are here to listen. Our existence is a temporary, luminous anomaly in a universe destined for darkness. The journey to the edge of the observable universe and the look into its ultimate fate forces us to ask the most profound question of all. Is this all there is? We have mapped the limits of our vision, but have we mapped the limits of reality? We have established that the observable universe is a finite sphere within a universe that is likely much larger, perhaps infinite. But what if the universe itself is not unique? What if our entire reality, our Big Bang, our laws of physics, our constants of nature, is just one bubble in an infinite, frothing sea of other universes? This is the concept of the multiverse. The idea of the multiverse is not science fiction. It is a logical and, in some cases, an inevitable consequence of our best current cosmological theories. There are several levels to this concept, each more mind-bending than the last, each one a potential destination beyond the scope of our current journey. The simplest level, the Level 1 multiverse, is simply the space beyond our cosmological horizon. Since the universe is likely infinite, there are an infinite number of other observable universes just like ours, far beyond the reach of light. The laws of physics are the same, the history is the same, but the arrangement of matter is different. Given an infinite volume, every possible configuration of particles must eventually repeat. In one of them, 10 to the power of 10 to the power of 115 meters away, there is a copy of you, reading this script, about to embark on the exact same journey. This is the most conservative form of the multiverse, a simple extrapolation of the infinite space we believe we inhabit. The Level 2 multiverse arises from the theory of cosmic inflation. Inflation suggests that immediately after the Big Bang, the universe underwent a period of exponential expansion. The theory of eternal inflation proposes that this process never truly stops everywhere. Instead, new bubble universes are constantly popping out of the inflating background, each with its own Big Bang. These bubbles are separated by vast, rapidly expanding gulfs of space, making travel between them impossible. Crucially, the fundamental constants of nature, the speed of light, the strength of gravity, the mass of the electron, could be different in each bubble. This is where the laws of physics themselves become variables, a truly mind-boggling concept. The very fabric of reality, the rules of the game, are different in each bubble. The existence of this Level 2 multiverse is a direct consequence of the most widely accepted model of the early universe. The most radical concept is the Level 3 multiverse, which stems from quantum mechanics. This is the many worlds interpretation, which suggests that every time a quantum event occurs, the universe splits into multiple copies, one for each possible outcome. Every decision you have ever made, every path you did not take, exists in a parallel universe. This is a universe where every possibility is realized, a staggering, infinite branching of reality. The sheer number of these parallel worlds is incomprehensible, a quantum foam of infinite possibilities. Finally, the Level 4 multiverse is the ultimate abstraction, the idea that every mathematically possible universe exists. If the laws of physics are just a set of mathematical rules, then every possible set of rules defines a real, existing universe. This is the realm of pure mathematics, where our universe is just one equation among an infinite library of equations. Why is this relevant to our journey through the galaxies? Because the very fact that we exist to ask this question is a profound mystery. The constants of nature, the strength of gravity, the mass of the electron, the ratio of the electromagnetic force to the strong nuclear force, are all exquisitely fine-tuned. If any of these constants were slightly different, stars would not form, atoms would not exist, and life would be impossible. A slight change in the strong nuclear force, for example, would prevent carbon from forming, and without carbon, there is no life as we know it. This is the fine-tuning problem. The multiverse provides a potential answer to this anthropic principle. If there are an infinite number of universes, each with different physical laws, then it is not surprising that we find ourselves in one of the very few that is capable of supporting life. We are simply in the one bubble where the dice roll of physics came up with the winning numbers. We won the cosmic lottery, and our journey through the galaxies is our prize. This realization brings us back to the human perspective. We have traveled from the Orion Arm to the edge of time, through 2 trillion galaxies, only to conclude that our existence is a cosmic lottery win. Our journey is not just a mapping of space, It is a celebration of the improbable conditions that allow consciousness to exist. The sheer scale of the universe, the violence of galactic collisions, the relentless pull of the Great Attractor, and the ultimate silence of the Big Freeze. All of these are mediated by the tiny, fragile spark of life that is capable of comprehending them. Our ability to look out and map the cosmos is the universe's way of looking back at itself. The journey through every galaxy is a journey into the nature of reality, and it is a journey that is only possible because of the collective effort of thousands of scientists, engineers, and dreamers who have built the instruments and theories that allow us to see this far. Our role, as the narrator and the viewer, is to bear witness to this grand, terrifying, and beautiful truth. We have completed our flight. We began in the familiar dust of the Milky Way, and we have ended at the wall of fire that marks the beginning of time. We have seen the universe as a dynamic, flowing entity, a local neighborhood locked in a gravitational death dance, a continent of galaxies streaming toward an invisible attractor, and a vast foam-like structure being slowly torn apart by the energy of empty space. The journey has been one of constant recalibration. Every time we thought we understood the scale, the universe expanded our definition of vastness. The sheer audacity of the cosmos has challenged our every assumption, forcing us to confront the limits of our perception and the power of our intellect. We started with the Milky Way, 100,000 light-years across, and felt small. We explored its structure, its barred spiral arms, and the supermassive black hole, Sagittarius, a star at its core, a gravitational behemoth that dictates the motion of everything around it. We moved to the local group, a few million light-years across, and realized our galaxy was just one of many, locked in an inevitable 4.5 billion-year collision course with Andromeda, a cosmic merger that will create the elliptical giant, Milkomeda. We mapped the Laniakea supercluster, over 500 million light-years across, and understood that we are all falling toward the Great Attractor, a massive, unseen concentration of matter that defines our galactic continent. This flow is a testament to the power of gravity on the largest scales. We traversed the cosmic web, a structure stretching billions of light-years, and saw the invisible hand of dark matter forming the scaffolding, and the repulsive push of dark energy slowly dissolving the entire structure, widening the voids and isolating the filaments. We looked back in time with the JWST, witnessing the chaotic, brilliant cosmic dawn of the first galaxies, challenging our models of how quickly structure could form in the early universe. We saw the universe transition from darkness to light, and we finally reached the cosmic microwave background, the 13.8 billion-year-old echo of the Big Bang, the ultimate horizon of our visible reality, the blueprint of all structure, and the final limit of our journey through light. The sheer number of galaxies we have flown through, 2 trillion in the observable sphere, is a number that defies human intuition. Each one is a stellar empire, a collection of billions of suns, planets, and perhaps other forms of life. And yet, the ultimate lesson of this journey is not about the number of galaxies, but about the nature of the space between them. The universe is mostly empty. The matter we see, the stars, the planets, the gas, the dust, and us, is less than 5% of the total cosmic inventory. The rest is the invisible scaffolding of dark matter and the accelerating engine of dark energy. We are the luminous foam on a dark, turbulent sea. The precise composition of the universe, a triumph of modern cosmology, is a chilling reminder of our own insignificance. 68% dark energy, 27% dark matter, and a mere 5% ordinary matter. We are the 5%, but it is in this emptiness that the true drama unfolds. The expansion of space, the stretching of light, the isolation of our future island universe. These are the forces that define our cosmic destiny. The universe is not a friendly, static place. It is a vast, indifferent machine operating on timescales and distances that make human history seem like a single, fleeting breath. And yet, here we are. We are the conscious product of this indifferent machine. The atoms in your body, the carbon, the oxygen, the iron, were forged in the hearts of stars that lived and died billions of years ago, in galaxies far, far away. We are literally stardust, the physical embodiment of the universe's history. Our journey through every galaxy is a testament to the human mind's capacity for wonder and its relentless drive to map the unknown. We have taken the light that traveled for 13.8 billion years and used it to write a story. We have used mathematics and physics to see beyond the visible, to map the invisible, and to predict the unimaginable. The universe is a mystery, and our journey has only deepened it. We have found the edge of our observable reality, but we have not found the edge of reality itself. We have mapped the galaxies, but we have not mapped the consciousness that is capable of mapping them. So, as we return to the familiar dust of the Milky Way, look up again. See the ceiling, the sky, the faint, familiar light. But now, see it differently. See it as the starting point of an infinite journey. See it as the brief, precious moment when the light of 2 trillion galaxies was still visible. The universe is a story, and we are the only ones here to read it. The journey is over, but the wonder remains. The universe is waiting.